Hi, this is Professor Stugard, and this is going to be our second video about multiple integrals. And this time we're going to look at our double integrals, but this time instead of just doing them over rectangles, we're going to look over more general regions. So first of all, the notation, if I'm integrating over a region in my xy plane, that's not necessarily a rectangle, we're going to call that D. And our notation is, well, basically the same as it was with the rectangle, except instead of an R for rectangle, we have a D for region. Okay. Oh well. Well, that's the convention. But it's the same idea. Now, when we're integrating over a general region, there's typically two types of regions that we can integrate over. And they're going to be set up in terms of our x's and y's. So our type 1 is where x is bounded by constants. If I can bound my x-axis between two constants, a and b, and my y, well, that gets to be more complicated with our functions. Well, this is a type 1 region, and we're going to set up a type 1 double integral. Now, in set notation, the way we would write this is, well, my region D is every ordered pair x and y such that x is bounded between a and b, and then y is bounded between these two functions. Now the key when we set up our integral is, again, we're typically going to be giving that notation here. We're going to have to put our bounds in. The idea is that we're going to have to integrate with respect to y first. That means the inside integral, when we do our iterated integrals, we're going to have to do it with respect to y first. And we need to make sure our bounds match up again. So again, the bounds for y are my functions, and then the bounds for x would be my constants. And we have to set it up this way. Now, type 2 is the same idea, but flipped. On a type 2, now we have y being bounded by constants, and my x is bounded by functions. Now, the thing you want to be really careful about, and again, this is just a place where it's very common to make some mistakes here, not because it's necessarily difficult, but because it's different, is that we typically don't write our functions in terms of y. And in this case, my x is bounded by functions of y. That means my variables are y. The variables of these functions are, again, well, like I said, y. And again, the way we would write our region in set notation, D is the set of all ordered pairs x and y such that x is bounded by these two functions and y is bounded by the constants. Again, we have that same general notation for our double integral, but now when we set up the iterated integrals, we have to do it with respect to x first. So again, here's my x. My bounds are going to be in terms of y, and then after we do that, then we'll do my function in terms of y for the constants c and d. And so again, the order is really going to matter, and you really need to take a lot of time in the beginning of these problems to understand what type of region it is and to set it up. This is a great 80-20 rule for mathematicians. For a good mathematician, 80% of the problem here should be setting up the region and the bounds. After that, it's all mechanical. After that, it's the integration and taking integrals and plugging in numbers and you know, the boring part, the mechanical, tedious part. 80% of your thought should be going into this step right here. Is it a type 1 or a type 2? Or, obviously, not everything's going to fit into those nice, neat categories of a type 1 and type 2. And so what we're going to have to do is subdivide our region into separate, smaller regions to kind of ease our integration. So again, in this example, figure A, that region D is not a type 1 or a type 2. I don't have nice, neat edges on either side. There's no way for me to write that out. So I'm going to have to subdivide it into region D and D1 and into region D2. And again, we're going to use this, again, with set notation, which is our unions, D1 and D2. And we're basically just going to have to set up an integral for the region D1, evaluate that, set up an integral for the region D2, evaluate that, and after we do both sets of double integrals, then we'll just add those results together with our union. And again, it could take a little bit of time to figure out that we're actually setting this up the right way. So let's take a look at our first example. So I have a double integral, 4xy minus y cubed dA over the region D, where D is the region bounded by y equals the square root x and y equals x cubed. So the first step always has to be to sketch the region. So I use technology to sketch this. I have the function y equals the square root of x in red and y equals x cubed in blue. The region bounded between those two functions is that part that I kind of shaded in green. We can see that they intersect at the order pair 1, 1 and 0, 0. So we have kind of a nice, neat, closed region here. And, well, how am I going to set up my integral? Is it a type 1 or a type 2? Well, the nice part is that this one can be set up either way. So as a type 1, the first thing I want to do is bound x by some constants. And I can see pretty clearly here that my region starts at 0 and ends at 1, which means x has got to be bounded by 0 and 1. Now I need to figure out, well, my region, how is that bounded now by my functions? So y has to be bounded by my functions of x. And so that's why I kind of drew that gray line in there. That's my region, right? I'm going to have to evaluate between those two lines. So which one is my bottom and which one is my top function? Well, hopefully we can see without too much difficulty here that the bottom function is my x cubed, the top function is my square root x, and so y is going to be bounded x cubed less than or equal to y less than or equal to the square root of x. Now, this isn't necessarily the only way I can actually set this one up. This particular one is kind of unique because I can actually bound this one as a type 2 region as well. As a type 2 region, I bound y by my constants. So again, I'm bounding y by the constants 0 and 1. And once I have that bounded by my constants, now I need to come up with my function. So what's my top function and what's my bottom function? Well, now, again, I'm measuring from my y-axis, right? My y-axis is between 0 and 1. So now measuring out from my y-axis, I'm measuring this way. And so my bottom function is going to be the red one. So my bottom function is y equals the square root of x. Except I can't write it that way because I need it to be a function of y. I need to find the inverse. And so the inverse is y squared. If I want to get x by itself, I got to square both sides. And y squared equals x is the same idea as y equals the square root of x. And so you're going to have to be able to, well, find the inverses of these functions. And none of these will be too algebraically difficult to find the inverses, but again, you have to take some time and think. 80% of the problem should be spent here on this step. And then obviously we do the same idea for the upper bound, which in this case, the upper bound is the y equals x cubed, which really means it's the cubed root of y. So now we can actually take our double integral and put in our bounds of integration and our notation. So we had our function, taking the integral with respect to dA, except we're going to replace that dA with the dy dx, except again, the order matters. We're doing this as a type 1, and so if I do this as a type 1, again, remember that means I'm taking that integral with respect to y first. Now, I can't split this up or do anything else really fun here because I just have to go term by term. So for the first term, 4xy, well, what's the antiderivative of y with respect to y? Well, 1/2 y squared. And then I can obviously simplify that because 4 times 1/2 is 2. And then the antiderivative of y cubed is, well, 1/4 y to the 4th. Now, you should pause the video and write this out and do the problem yourself. All right, and make sure you're following along. Make sure you're doing all this work out yourself on your own pieces of paper. And then, well, once I find those antiderivatives, and so I have 2xy squared and 1/4 y to the 4th, I need to evaluate at my bounds, my lower bound being x cubed and my upper bound being the square root of x. And again, be careful. Our intuition sometimes leads us astray here with what's the upper bound and what's the lower bound. But again, take your time, spend, again, 80% of your mental effort on setting up the integral and understanding the region, and the rest should hopefully kind of fall out. Now again, like I said, you should be doing this on your own paper. So obviously we plug in our bounds, we plug in our upper bound root x first, replace every y with the root x. And then for our lower bound, which is x cubed, plug in x cubed everywhere there was a y, and now simplify. And again, this is just tedious algebra. There should be almost no thinking at all. This should just be kind of the mechanical part of doing this problem. So simplify, combine like terms. We should get the integral from 0 to 1 of 7/4 x squared minus 2x to the 7th plus 1/4 x to the 12th dx. And again, if you didn't get there yet, pause the video, get there. And when you're ready, unpause the video, because I want to make a comment here that at this point there are no y's left, right? And there shouldn't be. Once I'm done integrating with respect to y, every y should have left this problem. And it should only be in terms of x's. If you still have a y left over, well, you missed something somewhere. And again, it is very easy to miss things in this class. There's going to be a lot of tedious problems, a lot of problems that take up tons and tons of space on your paper, but just be careful and work slow and be neat, right? The neater you can be, the better. There's so many times that I have to take off points because not that students didn't understand the concepts, but they didn't write things the right way. And especially when your bounds of integration are now functions, and sometimes more complicated functions, it can get a little difficult. Now again, I'm writing all these problems together in the same way, but of course, you can take that part in parentheses and go over and do that separately in your scratch work. Do that whole problem separately in your scratch work, and then after you do your scratch work, then bring it back at the end and plug it back into the integral so that we can actually take the integration. And again, at this point, it's a polynomial. This should be really, really straightforward in terms of finding antiderivatives. So again, find the antiderivative on your own. We're plugging in the bounds 0 and 1, so it's really just, well, subtracting and adding fractions here. And you should get the same answer I do. But do not move on until you actually check that you get that same result. All right, let's try a different example. This time I'm given my problem. Let's evaluate this double integral. So again, it looks like it's with respect to y first. My inner integral of my iterated integrals is going to be with respect to y. So again, I like to put my parentheses. And now, yeah, that idea is that, well, there's no adding and subtracting in my function, is there? Which means I can factor. It's with respect to y, so my x term must just be a constant. So I'm going to pull that constant outside, and now I just need to start with finding the antiderivative of e to the y cubed dy. Except there is no answer to this. There is no antiderivative for e to the y cubed. There's none, or at least non-elementary. Again, there's so many functions that do not have antiderivatives that sometimes mathematicians and scientists just create their own functions to describe what the antiderivative would be. But that doesn't work in our case because we're not professional mathematicians yet. And so, again, hopefully you had a good background in, say, Calc 2 when you did all of your approximations and you learned how to do Simpson's rule. And so you learned how to actually find an approximate answer for this integral, even if you can't find the antiderivative. But that's not what we're doing here, because we should understand the region first. We're not just going to give up and move on. We need to understand this region. So I graphed all the lines here. So again, my bounds for x were 0 and 3. My bounds for y were x squared as my lower bound and 9 as my upper bound. So here's the drawing. Now, which region am I integrating over? Which one of these regions is my actual region of integration? Again, take a second. Which one is it? What region is being described by that set of inequalities? You ready for the answer? It's that one, right? My lower bound for y is x squared. My upper bound is 9. So I need to be bounded between my x squared function and my 9. So that's my region. Now, wait a second. I have that written in my problem as a type 1, but I can write this as a type 2. How would I write this as a type 2? Well, first we need to bound y as a constant, right? Bound y by constants. And hopefully we can clearly see that y is going to be bounded between, well, 0 and 9. And then the question becomes, how do I bound x? Now again, this is the part that might not be intuitive at first. So take the time. I'm drawing some arrows here. X, right? That's a measure out from my y-axis. X is my measure out from my y-axis. And so when I'm looking at that region right there, well, where's that region bounded? Well, it's bounded between 0 and the square root of y. Don't forget, we're going to have to take our inverses. Right? When I write this region out and I take my inverses, it's going to be a function in terms of y. Which means I can take this problem the way it's written and actually switch it around. I'm going to switch around my dy and my dx here, which means I need to swap around my bounds. But again, notice that my bounds on the left-hand side were written as my type 1. The bounds on my left-hand side are written as my type 2. We don't just swap the bounds, we have to actually draw the region and understand it first. 80% of this problem is understanding the region. Well, once you understand the region, the integral should be fairly easy, right? We know that if I'm doing this with respect to x first, right? With respect to x first, anything with the y is a constant, so we can factor that out. And what's the antiderivative of x cubed? Well, 1/4 x to the 4th. And we evaluate at our bounds 0 and the square root of y. So again, that's not too bad. Factor that 1/4 as a constant out. Plug in the square root of y, raise it to the 4th power. Plug in 0, raise it to the 4th power, although 0 is always 0, so I'm not even going to waste my time doing that. And again, pause the video, do this yourself, make sure you're getting the same answer as I'm getting before you move on. Okay, so now we have that 1/4, that constant's all the way outside. Now I'm taking my antiderivative with respect to y, and again, notice there's no x's left in this entire problem. And so I have my integrand as y squared and e to the y cubed. So this, I might be able to integrate this. It's all in terms of y. Now, if your instinct says, ooh, I should be doing integration by parts, well, that's actually pretty good intuition. That is absolutely a technique we could use to try to tackle this problem. But always try the easy thing first. And the easiest thing to try with integration is always u sub. So u sub, again, doing a little bit of scratch work over here on the side. U sub means using basically the chain rule in reverse, which means I need to figure out what my u is. And my u is going to be my inside function, right? The chain rule and u sub are two sides of the same coin. So my inside function is clearly going to be y cubed. And then du dy is then obviously going to have to be 3y squared. And now, at this point, there are different techniques for how to continue with u sub. If you learn a different method than I did, that's fine. Just get the right answer, and I'll be happy. But what I try to do is try to match it up. Can I substitute everything exactly? Can I rewrite my expression with du dy to make a really easy substitution? And I can. I can see that 1/3 du is equal to y squared dy, so that I can get rid of the y squared and the dy, and all it's going to cost me is scaling it by a 1/3. And then also when we use u sub, don't forget to change your limits of integration. If y is 0, and I plug that in, 0 cubed is, well, still 0, that's nice. But when y is 9, if I plug that in, y to the third, or y to the third, which is 9 to the third, is 729. And then we make our substitutions. And again, do this on your own paper, but just check your answers with me. That turns my 1/4 in front into a 1/12. My bounds go from 0 to 729, but the antiderivative of e to the u du is just, well, e to the u. So plug in my bounds, e to the 729 is just e to the 729. There's nothing fun going on there. E to the 0 is 1, and really that's as simplified as we can make this particular problem. So again, make sure you understand the regions before you start just trying to throw some calculus on your paper. All right, so we've talked about our double integrals a bit now. Now, the nice part is when we do double integrals, we can split sums just like we split single integrals. So again, basically all that means is I can integrate piece by piece, and I can also factor constants. I already did that, and again, if you remember anything from Calc 1, yeah, we can factor constants. We can still do that with our double integrals. The one thing that we are going to be making use of a few times throughout this course is the idea of integrating over the constant function. So the constant function would just be the function, well, 1. But if I have a double integral of just 1 dA, remember that my function, my integrand, is really f of xy, which really represents my height. And if I have a constant function of just 1, that means I have a constant height of 1. And again, the context is that I'm talking about volume. So if this is volume, volume is your base times your height. Well, my height is 1, so it's just my base. And my base is just, well, d, my region d. So the integral of my constant function is just going to be the area of d. And we do have, well, notation for that, which is a of d. And that stands for my area of that region d. And again, this is very similar to when we were doing Calc 1. If I had a single integral from a to b of just 1, again, that's the constant height of 1. If I'm finding the area under the curve from a to b, that's my rectangle. But my rectangle has a height of 1, so really the length of my rectangle, which is b minus a, is just going to be the area, because it's going to be b minus a times 1. And that's it. All right, so again, as always, take your time, work through a couple examples, practice this, and make sure you're spending a lot of time sketching these regions. It doesn't have to be a beautiful sketch. It doesn't even have to be perfectly to scale. But be careful, because you can miss things if your graphs aren't good. If your windows aren't good, if your scales aren't right, you can miss some things. Take the time to make sure everything is, well, in the right place, set up your bounds, and hopefully things will go well for you. If not, always feel free to send me an email, and good luck studying.